When you hear the word derivative, you may be intimidated, but it can actually be pretty simple. A derivative is just the slope of a curved line. However, a problem that we run into is that the slope is constantly changing. As you can see, the slope of the line at this first point would be positive, and at this point, it would be negative. In earlier math classes, you dealt with lines that had an unchanging slope, or put simply, straight lines. In this example, some of the points in the graph of the line 2x plus 1 are plotted. By using the formula for slope, which uses 2 points, or getting the slope from the equation of the line, it can be easily found that the slope of this line is 2. Unfortunately, this technique cannot be used on the graph of a curved line. This is because at each point, the slope is going to be different. So instead, we must find the slope of a tangent line at each point, which are drawn in pink, in order to find the derivative at each x value. I'll explain this a little further. In the yellow, you can see using the slope of 2 points will not give you an accurate representation of the curve. A tangent line, in the orange, would be a much closer approximation to the slope of the line at point C. Unfortunately, if we use the x and y value of point C in the equation for slope, we will get 0 divided by 0, which is indeterminate form, a fancy term that just means impossible. In order to avoid this problem, we can move the 2 points A and B so close together that they basically become point C. To do this, we must take the limit of the equation as A approaches or gets closer to B. Don't freak out if you're new to calculus and are asking, what in the world is a limit? It's just where the graph intends to go. By plugging in the equation of the line and the point C into the definition of a limit, shown in white, we will be able to solve for the derivative. Here's a basic example. Given the graph x squared, we need to find the derivative or slope of the line when x is equal to 2. We can do this by plugging in our given values into our limit definition. Here we have f of x, which is just x squared, so we can plug that into our equation. Then we have f of a, which is really just the y value, so we plug 2 into our original equation and get 4, which goes there. Then we plug in x and plug in our a value, which is also 2. Now we can simplify. After simple simplification, we can plug 2 into our limit and solve for the derivative. So the derivative of the graph x squared when x equals 2 is 4. Now here's a real-life example of a derivative. Let's say that a college picks you to be the quarterback of their new team. It might be important to know how fast and how hard you can throw the ball, and you can use derivatives to find out. Using a line to show the motion of the ball, we can see how derivatives come to play in real life. At the beginning of the throw, the ball is moving very quickly, and its slope is increasing at a quicker rate. But as the ball reaches the full height of its travel path, the slope is going to slightly decrease until it reaches 0 at the very top. Then when the ball begins to move back towards the ground, the speed is going to increase and the slope is becoming steeper, but negative. We would have to find the derivative because at each point, the slope is going to be different. And there you have it. See, calculus isn't so bad.